So far this chapter we've been looking at series and trying to determine whether they converge or diverge. And we're going to expand on that a little bit and look at what are called power series. The first thing I want you to notice before any of this is that there's a variable in here now. So remember, we're summing over n. So each term, n indicates the zero term, first term, second term. But now there's also a variable. So this isn't really just one series. It's infinitely many series. Every time you plug in a different value for x equal 5, you get a series. X equal negative 18, you get a series. X equal pi, you get a series. So really this is infinitely many series. And depending on the x value, the series may converge or it may diverge. So what we're going to be looking at is, for a given power series, when is it defined, or when will it converge? Which x values will generate a series where that converges? The reason we are looking at power series specifically is that I mentioned previously our goal to get to Taylor series, these series representations of functions. And Taylor series are a type of power series. So we're going to start general, and then we'll zoom in on Taylor series after this. So this is what a power series looks like. This is a c sub n here for coefficient. And then you have these terms. And notice it's going to look like a polynomial, right? You're going to have this x minus a term to the 0 power, so a constant. So if we were to just start to write this out here, when n is 0, you just have that first coefficient, because that whole thing is 1. And then next, you would have c1 x minus a to the first power, then c2 x minus a to the second power. And if you stopped anywhere along the way, you would just have a polynomial, right? That is, these are constants. These coefficients don't have any x's in them. They might have a formula that generates them that's based on n, but there's no x's hidden in those coefficients. So this is a polynomial, but the only difference is this polynomial doesn't stop. There's going to be a third degree term, fourth degree term, fifth degree term, on forever. So it's a series that looks like a polynomial. So think of it as an infinite degree polynomial. And because of this, just like a polynomial, you could think of this as a function. There's an input, x, so you plug in an x value. And a is just some constant. We call it the center. And we'll see later on why centering it at different values is important. But a is just some fixed value. So you plug in different x's, and you may or may not get an output. If it converges, there's an output, the sum of the series. So there are inputs, x's, and there are outputs, the sum of the series. So you could think of this as some function. c0 plus c1 x minus a, and so on, if we were going to use some function notation. And what we're interested in, previously I said, we're interested in the x values that make this converge. So another way of saying that is we're interested in the domain of this function, right? The domain of a function are the values you're allowed to plug in and get something out, right? So there's going to be x values possibly where the series diverges, so there's no output. So it doesn't exist for those x values. So we'll be looking at trying to determine the domain of this function, or another way of saying it is the x values for which that power series converges. One thing to note before we go any further is I'm intentionally writing this out the long way because there is something hidden in this definition. If x equals a, this is 0. And then you have 0 to the 0, which is undefined, right, for n equals 0. So what we mean in this notation for n equals 0 is just that first coefficient c0. So if we happen to be plugging in a, we don't think of this as undefined 0 to 0. When x is a, doesn't matter what x is, that first term is just c naught. So in case you wonder about that. Okay, so on the note of plugging in a is a very important point for power series because what happens? So think of this function. What happens at f of a? Well, here you're going to have 0 to the first power, and then 0 to the second power, 0 to the third power, and so on. So because of the way we write a power series with this centering, there is one x value that every power series converges for, and that's a. Because when you plug in a, you get a minus a minus a. Every term goes away except for, and this is what I was talking about, that one is not 0 to the 0. It's always just that c naught. So you'll have just c naught. So in our hunt for finding the domain of this function, or the x values for which that series converges, there's one value we really don't have to worry about, and that is the center. Every power series converges at its center. So let's note that here. Every power series converges at a. Converges for a, however you want to say that. So let's just look at one really simple example of a power series. And it's actually so simple that we will be able to figure out when it converges without doing much work at all. Typically, it's going to be a little bit more involved than this, but it makes for a very nice first example because it's a special type of series. So let's look at the power series where all of these coefficients are 1 and the center is 0. So there's really no minus on all the x's. So all the coefficients are 1 and it's centered at 0. About as nice as you could make a power series. So it's really just the sum x to the n. If we were to write this out longhand, that first coefficient is just 1, then it's 1x squared, 1x cubed, and so on. Now, what's very nice about this is that we know how to handle this series because it's just a constant to the n, which is a geometric series. So we know that this is a geometric series. And we know geometric series converge when the absolute value of r is less than 1. And our r is x in this case. It's some arbitrary value. So for absolute value of x less than 1, remember the radius and absolute value being less than 1, not the radius, the, what would we call that, the common ratio, right? R from our geometric is x. We know that this series converges, and as a bonus, and we won't usually get this in power series, we know what it converges to, right? It converges to, remember the formula from geometric, a over 1 minus r. A is the first term, so that's the 1. And our r is x. So what we've done is we've taken a power series and we've actually figured out when it converges. We found the domain of that function, if you like. So let's write this down here. If we think of this as a function, we know when it converges. And we can actually express its sum in a closed form. What I mean by closed form is there's no dot, dot, dot. There's no series there. It's this nice algebraic form. And we know when it's true. You're allowed to plug in anything less than 1 an absolute value. So every x you plug into here generates a different series. And if you plug in x is less than 1 an absolute value, you get a convergent geometric series, and it equals 1 over 1 minus x. So if you plug a half into there, you're going to have 1 plus a half squared plus a half cubed, and so on. And that series equals 1 over 1 minus a half, or 1 over a half, or 2. So we could evaluate different values of this function easily with that formula. Now this is very nice because this turns out to be geometric. Not all power series are geometric, unfortunately, for us, because these coefficients can have n's in them. These coefficients are a function of n. Here, all the coefficients were just a constant, so n did not appear anywhere other than that exponent. But in general, we will have to take a different approach. We will be able to determine when it converges and when it doesn't, but we will not have this nice closed form for what the sum is. That we only get because this is a nice geometric series. So we'll look at an example next time of a power series that is not geometric, and how do we go about figuring out what x values will make the series converge. So we'll look at that next time.